Okay, so welcome to the makeup lecture on eigenvalues and eigenvectors. And in this lecture, I'm going to tell you what these things are, as well as how to compute them. And so there are many ways to introduce this, and I'm going to start with considering a geometric question. So, if I have an n by n square matrix A, then this is a linear transformation from Rn to Rn. And what this does is it takes a vector in Rn, let's say v, and when you hit it with A, you get some other vector AV also in Rn. And typically, AV has a different magnitude and direction from V. So AV can have different magnitude and direction from V. And the question I want to look at is, given a linear transformation like this from Rn to Rn and n by n matrix, is there a vector whose direction doesn't change? Is there a vector v such that v and AV have the same direction? Okay, so pictorially, I'm looking for a vector. Maybe this one didn't work out. I'm looking for some vector v such that when you hit it with A, it gets mapped to some vector that points in the same direction. And mathematically, what this means is that AV is equal to CV for some scalar V, scalar C. Okay, so let's look at this question in a few specific examples. So let's start off with a really simple one. Let's consider the matrix with diagonal entries 1 and 4. This is a linear multiplication by this matrix is a linear transformation from R2 to R2. And it's pretty easy to see what it does, to describe what it does in words. It multiplies the x coordinate by 1 and the y coordinate by 4. So as I said, in general, if you plug in some vector, like let's say x equals 1, 1, and hit it with A, you'll get some vector, in this case 1, 4, which doesn't point in the same direction as A. It's not as x. It's not a scalar multiple of x. But in this case, it turns out there are some special vectors. Okay, so until now in the course, we've been treating all vectors, democratically and equally. But now we're going to find out that there are some special vectors if you care about this linear transformation. In particular, if you start with the vector E1, and apply A, well, what happens? It's just going to be the first column of A, which is just E1 again. So AE1 is equal to E1. So the direction of E1 did not change when I applied A. And similarly, when you look at E2, this time you get that AE2 is the second column of A, which is 4 times E2. Okay, so it did change the vector, but it just stretched it by some number, which is 4. Okay, so in this case, E1 and E2 are special. By special, I mean multiplication by A is just scalar multiplication for these vectors, for E1 and E2. Okay, let's look at a slightly less obvious example. Let's consider the matrix with entries 0, 1, 4, 0. Again, a linear transformation from R2 to R2. And here, again, the question is, are there any special vectors? Well, let's just plot a few vectors. So if you see what happens to E1, in this case, well, AE1 is the first column of A, so the AE1 is actually 4 times E2. So in particular, it's not pointing in the same direction as E1. So this is not a special vector. And again, if you plug in E2 here, you'll see that it gets mapped to E1. Okay? So the same vectors that were special for the first A are not special for this one. Their direction gets changed. And so you can ask this question, are there any special vectors at all? It's not obvious that there are, right? What this linear transformation is doing is swapping the two coordinates and multiplying one of them by 4. It's not obvious that there's some vector whose direction is fixed by this. But it turns out that there are some such vectors. So in this case, I'm just going to show you what they are for now. So if you consider the vector v1 with entries 1, 2, okay? So maybe a better drawing is this, okay? Then let's see what happens when you hit this with A. Well, you just get 2, 4, which is twice 1, 2. So actually, this vector's direction doesn't get changed by A, it just gets scaled by a factor of 2. And similarly, you can check that if you look at the vector v2, whose entries are minus 1 and 2, then this gets scaled by a factor of minus 2. So AV2 equals minus 2v2. Okay. So in this case, hidden in this matrix, there were these two special vectors. Okay. So this leads us to the main definition of this lecture. Here's a definition. So if A is an n by n matrix, a scalar lambda is called an eigenvalue of A if there is a vector v that's not 0 such that AV is equal to lambda v. Okay, and this vector is called an eigenvector. Okay, so we're really switching gears now. Until now in this course, pretty much everything we've done in this course is in some way related to the equation AX equals B, which is a linear equation in which the unknown is X. And now we're going to look at this other equation, AV equals lambda V. And this is fundamentally different. Okay, so in particular, this is a nonlinear equation because the unknowns, lambda and V, are multiplied by each other. Okay, so given an A, finding eigenvalues and eigenvectors, it's not a linear equation. And the other thing I want to say about this is that we never consider the 0 vector as an eigenvector, okay? Because that's not interesting. For any matrix A, if you look at A times 0, you just get back 0, okay? So it's never 0. And as before, the conceptual meaning of this is that for an eigenvector, A is just scalar multiplication. And the number by which it's scalar multiplication is the eigenvalue, by the eigenvalue, lambda. Okay? Okay, so to give you a better handle on this, I want to make some remarks about how eigenvalues and eigenvectors are related to each other. Okay, so remarks. The first thing I want to say is that every eigenvector has exactly one eigenvalue. So every eigenvector corresponds to exactly one eigenvalue. What I mean by that is that if you fix some v and you tell me that AV equals lambda v, which is what's required to happen for v to be an eigenvector. Okay, you can't have an eigenvector without an eigenvalue. Then this lambda is unique. Okay, so the proof of that is rather straightforward. The proof of that is just, well, suppose AV equals lambda v. Okay, so what that means is that there's this picture here, and you had some vector v. When you hit it with A, it got stretched by some factor to get lambda v. Okay, and now suppose it's equal to lambda prime v for some other number lambda prime. Okay, well, what that means is that then lambda v equals lambda prime v, since they're both equal to AV, which means lambda minus lambda prime times v is equal to 0. But now remember that v is not 0, so that means lambda minus lambda prime is equal to 0, so lambda is equal to lambda prime. And in the picture, what it's saying is that, hey, we said that v is this special vector, so when you hit it with A, it just multiplied by lambda. And I'm saying, oh, well, if you're now claiming that AV is equal to some other number lambda prime times v, then because v is not 0, these scaling factors better be equal. Okay? So for every eigenvector, there's exactly one eigenvalue. Not for, this is not, I'm not saying that for every vector there's an eigenvalue. Not all vectors are eigenvectors. But for the ones that are, there's exactly one corresponding eigenvalue. So on the other hand, for every eigenvalue, so if you fix lambda, there may be many v's that are eigenvectors. Okay, so let's figure this out. So on the other hand, there are many eigenvectors for each eigenvalue. So the simplest reason is that, well, if v is an eigenvector with eigenvalue lambda, then nothing changes if you look at the vector 2 times v, right? Then A times twice v is just equal to 2 lambda v, which is equal to lambda times 2v, right? So, if something's an eigenvector, all of its non-zero multiples are also eigenvectors, right? So non-zero scalar multiples are also eigenvectors. But let's look at this a little more systematically. Let's try to figure out, given a particular lambda, what does a set of eigenvectors look like? So given lambda, all the eigenvectors v corresponding to this eigenvalue lambda must satisfy what? Well, AV equals lambda v, right? So now what I'm going to do is I'm going to just observe that this is the same thing as saying that AV is the same as if I applied the linear transformation lambda times identity to V. Okay. Identity doesn't do any scaling by lambda is the same as applying the linear transformation lambda times identity, right? And this is the same thing as saying that if I now look at the linear transformation A minus lambda I, then this maps the V vector to 0. Okay. So this is just matrix algebra, properties that you learned in chapter 2. This is how matrix vector multiplication works. And now it becomes very clear that this is just a system of, this is just a homogeneous linear system, right? This is some matrix, A minus lambda I, and I'm saying that, hey, V is an eigenvector if and only if it's in the null space of this matrix A minus lambda I. Right? And of course, V is not 0. So not everything in the null space is an eigenvector, but everything except the 0 vector is. Okay? So now the point is that to find the eigenvectors corresponding to A, corresponding to lambda, you just find the null space of A minus lambda I. Okay? And of course, you ignore the 0 vector. And in particular, this gives us a structural characterization of what the eigenvectors corresponding to an eigenvalue are. So the eigenvectors corresponding to lambda form a subspace. Okay? And this is called the eigenspace corresponding to lambda, which is sometimes denoted E sub lambda. Okay? Okay, I should add and the eigenvalues corresponding to 0 and the 0 vector, right? Because 0 is not an eigenvector. Okay, so now let's move on to how do you actually find these things given a matrix. So now the question I want to look at is, given A, how do you find all eigenvalues and eigenvectors, right? So, when I started the lecture, I focused more on eigenvectors, right? I said, what are the vectors whose direction doesn't change? And these are the special directions. And so you might think that the right thing to do is start looking for these directions, right? Which are the directions that don't change when you apply A? But actually, it turns out, somewhat surprisingly, that the right thing to do is to first look for the eigenvalues. First look for the scaling factors, okay? So the key observation is the following. So from what I wrote on the previous slide, some vector v, or I'm sorry, some number lambda is an eigenvalue. Well, if and only if it has an eigenvector, right? AV equals lambda v for some non-zero vector v. Well, by what I wrote on the previous slide, that's the same thing as saying that the null space of A minus lambda I is not the trivial subspace, okay? So let's think about this for a moment. So I didn't say is not the empty set. I said is not the 0 subspace. Why? Because, well, the null space of any matrix contains a 0 vector, right? And so what I'm looking for here is I want some non-zero vector to fall into the null space. And as I discussed on the previous slide, all such vectors will be eigenvectors corresponding to the eigenvalue lambda. Okay, so we're saying we've transformed this question about being an eigenvalue into a question about a null space being non-trivial. Okay. Now, if you go back to the invertible matrix theorem, we had many different characterizations of invertibility, and one of them was that, well, a matrix is invertible if and only if the null space is the trivial subspace, right? So using that theorem, we see that this is equivalent to saying that A minus lambda I is not invertible, right? So if the homogeneous system A minus lambda I V has a non-trivial solution, then it's not invertible, right? And we're going to use the word not invertible a lot, so I'm just going to define an alternate term for it. It's the word singular. Okay, and now we finally see why we learned about determinants, or one of the main motivations for learning about determinants is, there tons of different ways to check if a matrix is invertible, right? You could do row reduction, and look at the pivots, or you could check if the columns are linearly independent, and so on. But in this case, we actually, what we're actually interested in doing is checking whether a whole family of matrices, which ones are invertible, right? So we're interested in, asking for which lambda is this matrix invertible. So we're considering the whole family of matrices, A minus lambda I. And so the most convenient way to check if, to figure out which matrices in this family are invertible is to use a characterization in terms of determinants. So a matrix is singular if and only if the determinant of A minus lambda I equals 0. Okay? And if you think back about what the determinant is, well, if you think about the formula, it's obtained by multiplying together the entries of the matrix whose determinant you're interested in. And so this determinant is actually a polynomial in the variable lambda, right? So remember, we're trying to figure out which lambdas are eigenvalues. And so, just to summarize, what we've just discovered is the following theorem, that a number lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0. Now this equation, this is called the characteristic equation of A. And this polynomial, determinant of A minus lambda I, as a polynomial in lambda, this is called the characteristic polynomial of A, denoted chi sub A of lambda. Okay, where lambda is the variable. And okay, so this is called the characteristic polynomial. And the connection is the eigenvalues of A are the roots of the characteristic polynomial. Okay? So this is pretty cool because we've nailed down our search for eigenvalues we've turned it into a problem we know how to solve, namely computing the roots of a polynomial. And as I said earlier, once you know the eigenvalues, we already know how to find the eigenvectors, right? So given an eigenvalue, the corresponding eigenvectors are just the null space of A minus lambda I, which you can find by row reduction. So if you put these ingredients together, we get a two-step strategy for computing eigenvalues and eigenvectors. The first step is find all the eigenvalues by solving the characteristic equation that A minus lambda I equals 0. So the lambdas for which solve this equation, those will exactly be the eigenvalues. And now, so let's say you do this and you find eigenvalues lambda 1 through lambda k. Right? Now the second step is for each eigenvalue that you found, find the corresponding eigenspace null space of A minus that eigenvalue times A. Okay, and this will give you all the eigenvectors corresponding to that eigenvalue. And by find the eigenspace, I mean find a basis for the eigenspace. And of course, you know how to do that. You know how to find the basis for the null space of a matrix. So this will become clearer if I work through some examples. So let me do that. So let's look at an example. So let's look at the matrix A. The entry is 2, 3, 0, minus 1. This is some linear transformation from R2 to R2. And I want to find its eigenvalues and eigenvectors. So as I said before, there are two steps. So the first step is to write down the characteristic equation. So first you consider the matrix A minus lambda I, which is going to be 2 minus lambda 3, 0, minus 1, minus lambda. And now the characteristic polynomial is the determinant of this matrix. It's a polynomial in lambda. So it's that of 2 minus lambda, 3, 0 minus 1 minus lambda. And if you remember from the chapter about determinants, well, okay, it's a 2 by 2 matrix, so it's, AD minus BC, so that's just going to be 2 minus lambda times minus 1 minus lambda. And this is already factored, actually. This is very easy. You don't even have to use the quadratic formula. So this has roots 2 and minus 1. Okay, so what that means, so the eigenvalues are 2 and minus 1. Okay, and this procedure is guaranteed to find all the eigenvalues because what we discussed a few slides ago is all if and only if. So a number is an eigenvalue if and only if it's a root of the characteristic polynomial. That's the characteristic polynomial. Okay, and now for step 2, for each eigenvalue, find the corresponding eigenspace. So let's look at the two eigenvalues. The first one is lambda equals 2. So in this case, what I'm interested in is E2, the eigenspace corresponding to 2. That's the null space of A minus 2 times the identity. So that's the null space of what matrix? Let's just write it down. So the original matrix was 2, 3, 0, minus 1, and I'm subtracting twice the identity. So I'm going to subtract 2's on the diagonal. Okay, so what is that matrix? Well, that's just the matrix 0, 0, 3, minus 3. And, of course, we could do row reduction here, but it's fairly easy to see that the null space of this is just a span of the vector E1. Okay, so in particular, this vector, which I'm going to call V1, is an eigenvector corresponding to the eigenvalue 2. And in fact, let's just check this, that, if we actually multiply our matrix by this vector, well, what do we get? We just get 2, 0. So you do indeed get 2 times the vector. Okay, so this actually turned out to be an eigenvector, so our method worked. But we're not done yet. We need to do the other eigenvalue. So the other eigenvalue is lambda equals minus 1. Here I'm interested in the null space of A minus 1 times the identity, which is the null space of the matrix 3, 3, 0, 0. Which, if you do a row reduction, you'll see is the span of the vector 1 minus 1. Okay, and again, you can check that this sneaky procedure we came up with actually works. If you multiply it out, you get 2 minus 3, and you get 1, which is minus 1 times 1 minus 1. Okay, so by doing this procedure, we've discovered this hidden structure in this linear transformation A, which previously was just a matrix with 4 numbers. We've discovered that, okay, actually this, if you give it the vector v1, just along the standard basis, it maps it to itself. And then if you give it the vector 1 minus 1, which I'm going to call v2, so let's call this vector v2, then it also doesn't, it just flips it, doesn't change the direction. Okay. In the examples that we looked at, we had a 2 by 2 matrix. So we had a 2 by 2 matrix, and it ended up having 2 eigenvalues and 2 linearly independent eigenvectors. Right. So of course there were, if you include all vectors, there are infinitely many, but each eigenspace, there's only one linearly independent eigenvector, and you can check that in this case the two eigenvectors were linearly independent. So what I want to conclude the lecture with is ask the general question, Q1, how many eigenvalues can an n by n matrix have? And the answer to this, so it may not be obvious from the definition, right? Ax equals lambda x, that could potentially be true for infinitely many lambda. But the answer lies in the way that we compute lambda. So recall that lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0. So another way of saying that is that lambda is a root of the characteristic polynomial determinant of A minus lambda I, which let's just write it out in terms of the entries of A. So let's suppose the entries of A are A11 up to AN1, ANN, A1N. And now that's A, so A minus lambda I is the same thing, but with lambda subtracted off on the diagonal entries. And the rest of the entries are the same. Right? So the eigenvalues are roots of this determinant. Now, this matrix in here has exactly n terms containing the variable lambda, right? So in particular, if I multiply it out, if you go back to the recursive formula for the determinant, if you multiply it out, you see that this characteristic polynomial, chi of A, chi A of lambda, this is some polynomial lambda of degree n, or degree at most n. That's all we'll need for now. Okay. Well, let's just say it's of degree n. So we multiply out all these terms. There are n terms containing lambda. If you multiply them out, the highest power of lambda that you're going to get is n. And now we're going to recall this sort of pre-calculus fact that a polynomial of degree n has at most n real roots. Okay. So in particular, that implies that the matrix A has at most n eigenvalues. Okay. Now, at this point, you might be thinking, so some of you might know about complex numbers, and we learned about them in this course, that polynomial degree n has exactly n roots. Yes, that's true, but then the roots have to be complex. So here, this at most n I'm saying because I'm insisting on real roots. And if you want the eigenvalues to be real, then in fact there are matrices that have less than n real eigenvalues. So let's look at an example of that. So consider the matrix A given by 0, minus 1, 1, 0. If you think about this for a moment, you'll see that this matrix is just rotation by pi by 2 by 90 degrees. So it takes some vector x and it rotates it by 90 degrees, pi by 2. And so let's calculate the eigenvalues of this matrix. Well, the characteristic polynomial is the determinant of A minus lambda I, so minus lambda minus 1, 1, which if you multiply it out is lambda squared plus 1. And now it's easy to see that this polynomial has no real roots. So A has no real eigenvalues. And this makes sense because just think about it, if it did, that would mean that there's some vector in R2 with the property that when you rotate it, by 90 degrees, you get a vector pointing in the same direction. But that's not true, right? So it makes sense because rotation by 90 degrees changes the direction of every non-zero vector. Okay, so there can't be any eigenvectors and there can't be any eigenvalues. But of course, I'll just remark this now. However, this equation does have complex solutions. So plus I and minus I are complex solutions. And we'll get to this later. We'll get to what this means later. Okay, but the point I want to make is that because the eigenvalues are roots of a polynomial of degree n, there are at most n of them. And now the last question I want to look at is how many eigenvectors are there? Okay, there are infinitely many eigenvectors, right? Once you have one, all scalings of it are eigenvectors. So the real question is how many linearly independent eigenvectors can an n by n matrix have? Well, there's a simple answer to this, which is, well, the eigenvectors are elements of Rn. So how many linearly independent vectors can you have in Rn? Well, at most n. So at most n. Okay, so if you just count all the eigenvectors together, there's at most n of them. But we can ask a more subtle question, which is given for a particular eigenvalue, how many linearly independent eigenvectors can it have? So Q2 prime. So given some eigenvalue lambda, how large can the dimension of the corresponding eigenspace be? So before I tell you the answer, let's just look at some examples. So here's a matrix, 2, 2, 2. Well, on the diagonal and zeros everywhere else. The characteristic polynomial of this matrix, well, it's the determinant of the matrix with 2 minus lambdas on the entries. And the determinant of a diagonal matrix is just the product of the entries, so it's just 2 minus lambda cubed. So eigenvalues, well, there's only one, it's just 2. And if you do the computation, you'll see that the eigenspace corresponding to the eigenvalue 2 is actually just going to be, in this case, the span of the 3 basis vectors. In other words, all of R3. And that makes sense because this linear transformation is just twice times the identity in 3 dimensions. So any vector that you apply it to, it's just going to scale it by 2. Okay, so in this case, the dimension of the eigenspace was 3. Okay, let's look at a related matrix. Let's look at 2, 2, 2. But now let's put a 1 over here and zeros everywhere else. So now again, you can check this is an upper triangular matrix. So the determinant is going to be the product of the diagonal entries, and again, the characteristic polynomial is the same. So again, the eigenvalues are just 2, which appears 3 times as a root, triple root. And now you can check that the eigenspace in this case is actually smaller. It's just the span of E1 and E2. So it's 2-dimensional. You can check that E3 is not an eigenvector of this matrix if you just multiply it out, but anything in the first 2 coordinates is. And so here the dimension of the eigenspace corresponding to its eigenvalue is 2. And finally, you could look at this matrix that looks like this. And again, you'll find it has the same characteristic polynomial. It has the same eigenvalues, 2. But here the eigenspace has dimension 1. Okay, so the point I want to make is that eigenspaces don't always have to be one-dimensional. Here you have higher dimensional eigenspaces and as well as one-dimensional. These are examples. And in fact, the other point that comes out of this is that these three matrices have this exact same characteristic polynomial. And so they have the same eigenvalues, but the eigenvectors, the sets of eigenvectors are very different. Okay, so you'll notice that in these cases, in this case, all possibilities took place, right? You had a three-dimensional, two-dimensional, and one-dimensional eigenspace. And you can't have a zero-dimensional eigenspace because if you have an eigenvalue, it has to have a corresponding eigenvector. So the general theorem, which I'll state, which you don't need to prove, is that if lambda is an eigenvalue of A, then the number of linearly independent eigenvectors corresponding to lambda, which is the dimension of the eigenspace lambda, is at least 1, because you have to have at least one eigenvector. And at most, the number of times lambda appears as a root of the characteristic polynomial. Okay, so this number is called the algebraic multiplicity, and this number is called the geometric multiplicity. And in the previous example, you saw that this was indeed the case.